Hi guys, here's Maciej. Today I would like to talk about Amiga 500 power supply. This is this heavy unit that delivers 2.5 amps on 5-volt line. I know that you can replace this one with a new modern power supply, but I would like to keep the old one just to have one setup that is as original as it gets. So in order to keep it, I just replace the caps, the IC and the power transistor just to keep things fresh. And well, that worked more or less. Let's hear what happens when I will switch on my Amiga. Yeah, this is this whining sound coming from the speakers. And we will try to get rid of this sound. But before we start, I just would like to do one more thing. Jesus. I would like to cover this part of this power supply with some tape so I won't touch it by accident, because this is the high voltage there. Just a bit of a warning: if you don't know what you are doing, I wouldn't touch power supplies of anything that has a high voltage in it, because you can get killed or you can damage your Amiga. I mean, these things are really not forgiving. And the other thing is that if you are going to play around with it, disconnect the plug always. Do not, switching off this thing is not enough, because it cuts off only one line and there are two lines like L and N, and you actually don't know which one it's cutting off. Depending on the country, depending on 20 other things, you might be cutting the wrong line and still get a shock when you touch things around when it's connected and theoretically switched off. Okay. Now to our whining sound. Let's have a look on the oscilloscope how it looks like. Okay, you can obviously hear how it sounds. Can I zoom in? Jesus. You can hear how it sounds, so I'll turn off the speaker. That's much better. It's an AC coupling, so we see only the changing part of the voltage. This is connected to the 5-volt line that goes to the Amiga. And we have 600 peak to peak and 200 Hertz. And the plan is to get rid of this ripple. And before we do that, we have to look at the schematic. And we will go through this whole process, and on the end, hopefully it will work. Let's have a look what we have here. This is the schematics of this power supply. Which is a good example. You see, there's this similar switch with this power supply. It's supposed to be switching off the line and the neutral. You just realize that I'm not showing what you should see. This is good. This is a good example. So the switch supposed to switch off the line and the neutral is connected non-stop, but depending how you plug in your plug or how the wires are actually wired inside your wall, those might be switched. This will switch off the power supply, but it could be that the line goes in here, you will touch it here and you will get a shock. Transformer, 2 rectifier diodes. This part is covered by a black tape, in my case, what we have seen. And let's have a look. So now here we have something like that when it comes to voltage, and it's about, 15 volts or so. What is important is that it goes into this power transistor. Now this chip generates a PWM signal that switches on and off this transistor. So now on the collector here on output, we have 50 kilohertz that goes through this choke. The choke gets rid of the high frequency, caps smooths it out, and it goes to Amiga. My power supply does not have this diode. The cap goes directly to the ground. I think that's really not important. It has this diode, so because the diode gets rid of this all generated stuff from this coil. Anyway, the problem is right now that this coil is great to get rid of the high frequencies like 50 kilohertz, but we have 200 hertz. And this coil is not picking this up. We would need a much larger coil, but obviously that's not the idea. I can't put a larger coil in there. I don't have one. So we will play around with the parts that are here to get rid of this ripple. I decided to divide this video into small parts. I will just join them together. It's just easier to shoot. So what we are doing right now, I have just disconnected this cable from Amiga and connected such cheap load. Let's power it on and see how this load is doing. It shows 4.4 volt, which is not correct, but the load is working fine. Let's have a look on the real voltage so that we can be sure that there is everything fine with this power supply. Only this Chinese load does not show the right value. So maybe this is due to the wire. There is a voltage drop across this wire. Could be. Really? No. Okay, let's decrease the voltage to the current to 200 milliamps or 100 milliamps, and at 100 milliamps it shows 4.8. What's the multimeter showing? Jesus. 5.0. I believe that whatever that means, the readings of these things are not precise enough. I'm going back to 1.3 amps, let's say. 1.3 amps shows 4.6 volts, and in reality we have 5.1. Very nice. And the current is fine as well. Let's check a look at the current so that we can be sure that our test setup is properly done. And the current is 1.4. The device is showing 1.3. Anyway, that is sufficient. So we have nice load on the 5 volt line, and we can continue with that without having to risk damaging my Amiga. And now let's have a look on the schematics. So we are interested right now into this chip. In this chip, let's have a look on it. That's the layout of this chip. Here we have oscillator that is generating the PWM signal, and on the right hand side we have output. Let's see where this output goes on our Amiga. First 14 and 11. So the 14 and 11 are going to the ground. Those are NPN transistors, which means that when they are enabled, they will short to the ground. Where goes 12 and 13? 12 and 13 together are going to the base of this PNP transistor, which means when they short to ground, they enable this transistor. So basically this is the PWM output that goes to this transistor and does switching. The thing that we are interested in is this comparator, but first let's have a look on the dependency between generated PWM signal and this ripple that we are observing, which means I will connect an oscilloscope probe. For example, like here, I could connect it as well here, but okay, I have just soldered one here. And the other one is on the 5 volt. Let's have a look on the scope. Can I zoom in? Whoa. Maybe not so much. That is nice. 1. Great. Let's stop it for... So what we hear, the yellow one is a ripple on the 5 volt line. And this is the PWM signal, and just take a look. The frequency and the duty cycle of the signal is constant. The only thing that is changing is that the signal gets switched off when the value on the 5 volt line is above some threshold, and then it's getting switched on when it's below some threshold. Let's play around with the load. I will decrease the load now. I'm decreasing the load, decreasing. As you see, the pulses are larger. When I increase the load, the pulses are shorter. Which means this is how it limits the current. It limits the current or the voltage so that it changes the pulse time in the generated signal. And my idea is to do something that the pulses here will get shorter but more frequent. Then I hope to get rid of this ripple. I'm a software engineer, I'm not electronics engineer, so maybe this is not the right thinking, but this is the path that I've chosen, and well, we will just follow it and see where it gets us. And I would like to talk about this particular op-amp. This is this chip right here, and what I would like to show you is how the input pins are related to the output, and how the output is related to the PWM on the collector of the power transistor. But the only problem is that I can't connect oscilloscope in here because it's inside the chip. So what I did, I took those two pins and I've connected this to external op-amp, which is right here on the bench. See? That's our op-amp. It's hidden in here. And now let's have a look on the scope. Okay, first I will show you the positive input of this op-amp. Take a look how it looks like. Now have a look on the schematic. That's the positive input of this op-amp. It's actually painted over there. So that's the correct one. Yellow one is number 9. That's the... So now we can see the positive and the negative input of this op-amp, and this is the output of this op-amp. And on the channel 4, I have the collector. Okay, so we have proven right now that the output of this op-amp is strictly related to the PWM signal on the collector. Which means, if we have a look on the schematics once again, which means that the outputs of this op-amp is more or less given on the collector. This one here is constant, this is just oscillator, and this one is changing. So the pin number 9 is something that we should concentrate on. Before we do that, however, let's have a look once more on the signal that we are getting with a little zoom, wherever it is. Now, this is the positive, maybe. This is the positive input of the op-amp. This is the negative one. Let's remove channel 4 because we don't care. This is the positive input of the op-amp. This is the negative input, and this is the output. So when the positive has a higher value, output of the op-amp is positive, which is plus 5 volt or something. When the negative input has the higher value, I mean, that's the negative. When the negative has the higher value than the positive, the output of the op-amp is low, which is ground in this case. Makes sense, looks fine. So in a second, I will meet you once more, and we will talk about this pin number 9, what we can do about that. Before we continue, I would like to have a second look on the voltage that this device is showing. So maybe there is a voltage drop across this wire, just to have things clear. Let's measure the voltage on the Amiga side, on the power supply side. 5.1. Now what the box is getting. .8, so the box is getting 4.8 and it's showing 4.7. So the most of the voltage drops across this wire. So I have to fix that later. Use a proper wire. It should be fine. Well, it's not that important for our case right now, but at least we know that what the problem is. Let's have a look now on the schematics. And so we know already that this comparator is responsible for switching, the input of this comparator is responsible for switching on and off the PWM generation. Now we would like to know which one of those comparators is leading one. Let's first have a look on this one on the right hand side. Now I have those two inputs that I can connect to the oscilloscope because this is pin number 4 and 5. However, I can't check the output in a separated way without having influence from this one. So once again, I connected an op-amp right here, and we can see the result on the scope. So you see here is a yellow and blue input. They are exactly the same value. So this is the inverting and non-inverting input of this op-amp. And this is the output, which is constant plus 5 volt. Let's have a look on the schematics. 4 and 5. 4 is going directly to plus 5 volt right here, so it's what goes to the Amiga, and 5 is getting also plus 5 volts through some static components. So in our case at least, this op-amp provides constant output, so it's not interesting for us. We will see that. We will take a look on the second op-amp in a second. This is the last part of our video, and now I would like to talk about this op-amp, what this one is doing, so that we have an understanding of what is going on at the pin number 9. And in order to measure this op-amp separately, I have once again prepared this test scenario where I'm using external op-amp and everything is connected to the scope. Let's have a look on that. The voltages are not related. I just moved things around so they do not overlap. But this is important. That's the input of our op-amp, which means that's inverting and non-inverting input. One is constant and the other one is a kind of sinus wave. And the purple one is the output of our op-amp, which perfectly makes sense. If it is above, then it's low. If it is below, then it's high. Doesn't matter which one is which. Let's have a look at the schematics. So one of the inputs is constant and the other one is kind of sinus wave, and then this one is switching on and off. And the pin number 9, it's the blue line. So basically this is the output of our op-amp and this is the pin number 9. So this is the output of our op-amp that is sitting on this board separately. So the output of our op-amp is, which is connected directly to the oscilloscope. But the output of the op-amp in this chip is the pin number 9 actually. It's output of this both op-amps. And this is what we can see here as a blue line. So we can clearly see that when the output is high, then the pin number 9 goes up, and when the output is low, then the pin number 9 goes down. So it's strictly related. Yes. Now let's have a look on the. I will move the channel 4 to collector, which is going to the coil, just so we see how those things are related. and the amplitude is on the collector much higher, obviously. This is number 4. What did I just connect? Okay, that's what number 3. And what about number 4? Okay, so obviously this is the collector voltage. No. This is the pin number 9. So if the pin number 9 is below some value, you can see that that it stops generating the PWM signal. So this is everything related. So let's switch back. Maybe. Let me think about it. So there is a clear correlation between the voltage value on this pin number 9 and the output that we're switching off of the PWM generator. Once again, I would like to switch back to the output of the op-amp. We can clearly see this is the pin number 9. What can we see here? Why this is jumping around? Obviously, when the output goes high, the value on the number 9 increases. When the output of the op-amp is low, the value on the pin number 9 goes down. This is exactly in the same way related to switching on and off the PWM generation. Let's have a look on the schematics. What is the input of the pin number 1 and 2? Can we see it? Yes, I think that we can see it. Pin number 1 and pin number 2. Both are getting some voltage. This is the one voltage here and one voltage here over exactly the same voltage divider. 0.47, 1.5, 4.7, 1.5. So, but the pin number 1, so inverting input. Now the pin number 2 is non-inverting input. Gets the value from the pin number 16, which is voltage reference. So this is 5 volt. So this op-amp has a voltage. This chip has a voltage reference that can provide a few milliamps of a perfectly stable 5 volt. So now we can see that on the pin number 2 we are getting 5 volt. I mean, divided through this voltage divider is a few hundred millivolts, but anyway, the division on the other pin is exactly the same. So basically this is our voltage reference that is going into this line of the op-amp. And now on the pin number 1, just let's forget this cap right now, but on the pin number 1 we are getting the plus 5 volt that is going to Amiga under, you can see it over there. So this is exactly the voltage that is going to the Amiga. So now this is called error correction. So when the voltage that is going to Amiga is too high, the op-amp switches, and when the voltage is too low, the op-amp switches again from plus 5 volts to ground. So this is called an error correction, and now we know why, because it's comparing the perfect 5 volts with the value that is going to our Amiga. The problem that I see here is this cap. I mean, this cap, what it does, it's obviously a feedback cap on this op-amp connected like so. But what it also does, when when it's charging, then it's short. So it provides 5 volt from the output directly to this op-amp. And to this op-amp, to the pin number 9. When this cap is charging, once again, the 5 volts from the output from the Amiga goes directly to the pin number 9. So when the cap is charging, the 5 volts from Amiga is connected directly to the pin number 9. So let's say that larger the cap, then so during the charge time of the cap, the error comparison, we can say it's disabled, right? Because it's shorts. It's like it makes a voltage follower from this op-amp. So the idea would be to replace this cap with something smaller, that we have more aggressive setup, so that we have more error correction. So we will try to use a shorter cap. Shorter cap will charge up quickly, faster, and it will charge up faster, so it will left more time for the error correction. Let's do that right now. And in the beginning, I will just remove this cap completely. Okay, what we don't need here. I will remove my external plus 5 volts right now. Jesus, that is hard. Okay, we don't need that anymore. And we can leave all the other stuff. It's just remove maybe a few things here. What I would like to have? I would like to have, let's say, on the channel number 1, I have to find the channel number 1, that's probably 4, right? So we don't care for channel number 4 right now, we can just throw it away. This is the channel number 1. We would like to have on the channel number 1 plus 5 volt. And maybe on the channel number 2, which is right here, the generated PWM signal. Okay, that I would like to cover so it doesn't short anything. Okay, that looks fine. Let's switch it on just to see whether the effect is as desired. And show it on the scope. Channel number 1, coupling is AC. We are interested only in this ripple. Great, 800 millivolts looks good. And channel number 2. Is the PWM signal going to choke. Great. Now I will remove the cap completely, this one from the error correction, just to see what happens if we remove it. This is really the good idea to use some load instead of experimenting with your Amiga, because who knows what that will cause. Okay, the cap is gone completely. I'm holding it right here. Power back on. Let's move down the PWM generation. This is the ripple on the 5 volt line. I mean, it's completely gone, as you can see. I will just connect the cap as it runs. At least I will try. This is with the connected cap. Not sure whether the iPhone is picking up this sound, but there is now the sound coming from the coil. Probably because we have increased the frequency with cap. And this is without. I'm trying to connect the cap. It's not that easy. Okay, now, Jesus, just stay connected for a second. Now the cap is connected. Ripple is back, and the whining sound is gone. Now I'll try smaller cap. That one is 15 nanofarad. Let's try. I have 2.2 at hand. Oh, 2.2 is actually not half bad. we have 300 millivolts ripple, and 1 nanofarad, how far would that get us? With 1 nanofarad, doesn't want to connect. Okay, and 2.2, I think maybe 2.2 was a little bit better. I mean, okay, so we have much. I will just solder in this 2.2 cap right now, because I think that the whining sound is not so noisy when we use 2.2, and with 1 it's much more disturbing. I mean, the sound is completely gone when I'm using 2.2. I'm just soldering it in. Okay, and let's power on. Peak to peak is 300 millivolts. It was 600 before, it's a half. Now, what we are going to do, we are going to remove the load, power on the real Amiga with this setup and see what happens. Okay, I have removed the load, I can power on the real Amiga. It's powering on. And I mean, there is still something coming from the speakers, but it's, I mean, the speakers are not the full right now, and the full volume, so it's definitely much better. Let's just try this 1 nanofarad cap to see, or maybe, I mean, that was actually quite satisfying. The only thing is that I still, okay, let's turn it down. I'm not sure if the iPhone is picking it up, but there is some whining coming from the coil. Very, very low volume, but it is there. What I can do, just have a look on the schematics right now. We can try out something else. For that I will connect the load once again here to the input. And just have a look what we have here. We have RT and CT. Those two guys are responsible for the frequency generation of this PNW. Let's have a look what is the frequency right now. I have connected the load and disconnected the Amiga because I don't want to play around when the Amiga is connected. Okay, let's stop it and let's measure the frequency of the PNW. Like 47 kilohertz or something. What will happen if we increase this frequency? We can increase the frequency when we lower the value of this resistor, because if you multiply the value of this resistor by this cap, I mean, you can read it in the datasheet from this chip. If you multiply those two values, this will give you the time of the single period. So lower the resistor value, shorter period, higher frequency. Let's replace 12K with 6. I mean, I have this resistor already here on the back of the board. So right there. So what I have to do is just to remove it, because it's connected from the mains, and use something smaller. I don't know, maybe this will help with the whining. If not, then we can stay with the cap that we have right now, because the whining is, I mean, the whining coming from the coil is actually not half bad, so I mean, it's much better than it was before, that's for sure. Now let's see whether the frequency has changed. This is the old snapshot. Now I'll let it run on the new frequency. And let's measure. I mean, we can see it already that it's a bit tighter, but second. This is where it starts. This is where it ends. 80 kilohertz. So we went from 46 to 80 kilohertz. Was it 46? Ah, doesn't matter. I think it was 46. Okay, and seems to be running. Switch it off. I will remove the load and power on the real Amiga with this setup. Let's see what happens. And let's see what will happen. We are ready. Does it go on? Yes, it does go on. There is just no sound at all. Holy crap. It's really working. Have a look on that. The ripple is 300 millivolts. Apparently not enough. The amplifier is full at the maximum. Just have a look on that. This is Amiga booting, and this is the knob of the amplifier. I've turned it completely on the right. It makes no sound at all. I mean, this is really suspicious. Has to be true. You know what? I would like to connect the mouse. Do I have a mouse? The mouse. Where did I use it? Just hold on a second. I feel that my mouse is in the second Amiga somewhere here. That's great. We are going to do it. Won't take much time, because I can't believe that the sound coming from the speaker is completely gone. It's like totally gone. I mean, it's a full volume. Okay, let it boot. Everything works as it should. Takes some time to boot, as usual. I'm going to play some music to really make sure. Obviously, I'm going not to play it on the full volume. To be sure that this whining sound is totally, completely gone. It has to boot twice because I have the newer Workbench version, and it has to load the Kickstart ROM. Okay, data. Pro Tracker. Crap, I sorted my music. Okay, fav. Doesn't matter which one. There is no whining sound coming from this thing at all. It's totally Jesus. Okay, that worked. It's really working. This is our solution. 2.2 nanofarad cap, and the resistor, which is half value of this one, is 6K. Okay, that was cool. Great. Thank you for watching, and bye. Have a nice day.